Hi everybody. Thanks so much for coming today for the next seminar in the Robot Learning Seminar Series. I'm very happy to introduce Markus Wulfmeier from Google DeepMind. Markus has been working on a lot of really exciting projects from DeepMind at the intersection of robotics and reinforcement learning, particularly relevant at the moment because of the Euros. So those of you thinking, who can possibly beat England this year in the Euros, and you're wondering which human team might beat England, don't worry, because there's some robots coming who might stand a chance one day. And yeah, on that note, Markus, thanks so much for joining us, and over to you.
All right. Thanks, Ed, for the kind introduction. We'll come to robot soccer in the second half of this talk. I'm known to run over a little bit. I'm going to start the timer for myself. If you have any short questions throughout, please feel free to ask. If there's something bigger, something that goes a little bit more exploratory, we can try to squeeze this in towards the end. I'll try to squeeze the talk into 40 minutes and then we have a bit of time left. But let's see. Okay, so hi everyone. My name is Markus. I'm a research scientist at DeepMind in machine learning and robotics, and most recently also in other applications with kind of real-world contact. So I'll be talking in the beginning also quite a bit about the project on the right, which was a fantastic collaboration with folks at Google Maps, an app that many of you might know on your phones. And the big question for us is in the context of reinforcement learning right now, where larger and larger amounts of data become available and also are becoming the foundation for more and more general agents, more and more capable ones. Where does this leave reinforcement? Reinforcement learning, classically, we've been working a lot in settings like learning from scratch, solving partially also toy tasks. Where does reinforcement learning sit when we already have very capable agents to begin with, or very large data sets to begin with? And one of the perspectives that you can see this from is if you look just at, like these figures are slightly out of date, but if you look at the examples from like images and text data, we're now moving into a scale of billions of images, and this was like 3-4 years ago. Text trillions, by now many of those. It's just an enormous scale of knowledge that we have access to. In robotics, we're still sitting at the scale of maybe a couple of millions, and that with some constraints of using a lot of simulation data. And it's really the question of, when we look at robotics or other applications with regard to real-world control, embodied AI, how do we get to a similar scale? And this is exactly where I would like to loop in regarding reinforcement learning. On two aspects where reinforcement learning actually can still enable us quite considerable scale or scale gains. In particular, one of those is obvious. That's the one that we've already been working with for years and decades regarding just playing from scratch. RL is a data generator. RL is a mechanism for collecting data in a way that continuously self-improves kind of. And in that regard, we'll talk a little bit about robot soccer, which will be in the second half of the talk. And on the right, you see the example from Google Maps, where it's actually about using existing data. And you can see it very simple. Let's first say research is always a village. Like, I'm presenting the work of many, many amazing people on this slide from Google DeepMind, Google Research, Google Maps. And for many of the questions, it might be actually best to refer you to them, but I'll try my best during this talk. So let's first talk about scaling regarding data usage, regarding RL as an optimizer. And the most standard or the most intuitive example that I can give you here is the example of behavior cloning, so maximum likelihood on all of your data, just imitate everything, versus offline RL. See it as like filtered doing of everything. If you can do offline RL in comparison to BC, and this is work by a couple of colleagues led by Toby Springberg, Abbas Abdul Maleki, Jingwei Zhang, Oliver Groth, and Michael Blush, and Thomas Lampe, then you can suddenly access much, much larger data sets. Suboptimal data. Very often when you have suboptimal data, that doesn't mean that everything in the data is bad. That actually means that the overall trajectories that you have, they're not as good as the other data that you have. But maybe parts of that data enable you to get into a state space where other demonstration trajectories can help you to succeed. So if you can scale up the amount of data that you use just by opening up the space to use different data sources, you're in a really good space here. The figure on the top just kind of shows this with regard to specific performance in, let me think, these were some robot stacking tasks, just with respect to the amount of compute that you invest. So that's the other important thing right now. The more we scale the amount of data that we use, the more it also matters how much compute we invest. So it's not just about the data that you use, but actually the overall compute that you need to invest to use that data. And here's nicely shown that with differently sized models, perfectly scarce between like 30 million and 1 billion parameters, with PAC, which is an offline RL method here in comparison to BC plus some auxiliary losses, you get really good gains across the spectrum, no matter how much compute you want to invest in this. But I focus my main attention in this part not on the use of other data that you otherwise wouldn't be able to incorporate into your systems, but on the ability to extract different information from data. In particular, I'll talk now about our work on inverse RL, this collaboration with Google Maps. Really a big shout out to Matt Barnes and Matthew Abuk, who were leading this project. Well, yeah, the website you all know, more interesting work is on the paper for you. But if you've used that website, if you've been using Google Maps at any point recently or before, you know the setting. You want to get somewhere, how do we get there? Usually when you drive a car, you mostly care about speed, but imagine you're on a bike, you care about a lot of other things. You might care about how busy is that road, how noisy is it, the quality of the street. There's many other features that can describe your path that define how likely it is that you take it or how much you would like to take it if you don't know about it in the first instance. And so this problem of route optimization, we can describe it as a Markov decision process. We can solve a problem as MDP with RL, but inverse RL says you actually don't have a reward function to begin with. It actually says what you have is demonstrations. So now think about navigation in Google Maps. There's actually lots of people navigating constantly from one point to another. There's conceptually a lot of data available that you can learn this from, and you can figure out why people move a specific way from A to B. This is a super complex problem if you look at it. I'm going to simplify it drastically throughout this talk. There's a lot of noise in the data. There's a lot of confounding aspects where, I don't know, you look at your phone, you get a suggestion from Google Maps. Even if it's not the optimal for yourself, you might still take it because it's the one that you see. So from a data noise and cleanliness perspective, this is very hard. I'll be ignoring most of this, but just go down to the core of this problem. And this was a really exciting opportunity to scale some of our fundamental ideas. So I've been working on inverse RL since the beginning of my PhD, like about a decade ago, to really just world scale. We suddenly have like 200 million states, 360 million actions, 100 plus million demonstrations. So there's a lot of information to get really exact models about what people prefer. And then we can kind of like lead this back and learn preferences, and based on that just suggest to people what would be a good path. And just to go a little bit back to where the foundation of this sits, classically, when you use Google Maps, there's a couple of numbers that engineers have kind of like tested over and over that says like, people like to be fast when they get somewhere. Like, you like to spend little time. And you don't like, I don't know, noisy roads and so on so much. So there's a couple of, let's call them magical numbers in your code that get a little bit optimized throughout time. But if we do this in a data-driven way via inverse RL, we can actually get something much better. In the context of this project, then we went through a couple of interesting method improvements, just because you need to scale methods that are inherently really hard to scale. Let's see, to keep this very high level, at its core, we've presented a new inverse RL algorithm, receding horizon inverse planning. I'll talk about that in a moment. And then really a couple of strong engineering improvements in the context of how to shard this problem effectively, how to split the load across a distributed training system. I will not be talking about that. If anybody has questions, I'd be happy to forward you. It's a super interesting problem, but I'll be just less suited to talk about that. And then further improvements on graph compression, initializations for the algorithm. But let's talk a little bit about the algorithm. So classically, when you want to do inverse RL, it means that you solve an RL problem in the... Okay, go ahead.
Can you just define what inverse RL is as opposed to RL?
Perfect, I'm going exactly there right now.
Right, fine.
If you solve inverse RL is you don't have a reward function, you try to infer that reward function. The setting is you have a bunch of demonstrations and you train an agent so that the agent's behavior looks like those demonstrations. This kind of optimization is mediated via the reward function. that you kind of optimize throughout the process. And you can now imagine this as, or like the easiest way to see this is you train an RL agent. After that is converged, you see where that agent goes. You see how that differs from what your demonstrations are. Based on that, you give your reward function and then a nudge. One gradient step on the reward function. And then you solve the whole RL problem again. And give it another nudge. So you can see that this is like super expensive to run. And there's lots of improvements that are needed. One of the aspects is that we can do this really accurate in a nice probabilistic way. We can describe it very exactly in terms of which states with which probability the agent visits. And there's a lot of work in this context for maximum entropy inverse RL. And there are other approaches that go more sampling based, where we draw individual trajectories. So the right one works actually quite well on deep learning as well. And this is some of my PhD work in that space. But this is super expensive. And then we can do something sampling based. Just roll out a couple individual trajectories, and based on those, I can also update my reward function. So we have something that's either very accurate and highly computationally expensive, or like quite cheap, but inaccurate. But also, in particular, a lot of people have been working in this space before. The sampling-based approach, the sampling-based realization, let's say, is super hard to stabilize for deep learning. There's still not a really good understanding for why that is, but for now we're in that space. So the simple thing that we've done is really just say, there's a horizon up to which we do this probabilistically, and we can adapt this horizon however we want to see fit regarding a trade-off of accuracy and computational requirements, or on the other side, we just then run sampling-based. I will show you results in a moment, but okay, let's go. Sure.
The idea of running sampling-based forward, would it be a better idea to maybe use like an explainability mechanism in order to make more of an informed next step inference rather than just having a purely randomized sampling-based approach, like after a certain step?
Yeah, it's not random sampling. It's guided by the reward function at that point in time. So it's somewhat informed, but I fully agree that there could be better things to be done in that space. And also maybe as a full disclaimer, this method we found to work really well in that setting. Definitely doesn't mean it's the best thing. It's a great space for exploration. If somebody's interested in that space, please bring it afterwards. Okay, so if we train a model, then we can get improved recommendation of paths because now we have a better presentation of the preferences of people. And then, like, if we have preferences, we can just run a plan around this one. We can just run A star, we can run die star, whatever you want. But what we can also do, in addition to just getting now nice predictions, is we can look back at our data. We can look back and actually say, how well does this model now agree or disagree with the numbers that previously our engineers have very painstaking work assigned to different features? And what you actually find is that we can use this to clear our data. Excuse me. So this is quite interesting. You have, for example, the bit here on the top from Nottingham. I think this is, I'll skip the one below, but the one above deserves a bit of attention. If you look at the image for the preferred route, you see a gate, right? This gate is open in this picture. So the thing is, this gate is actually always open. It's annotated as a feature in our data as it's a gate, without further information, without open or closed. Therefore, if it's a gate, people don't drive there, or drive there very seldomly. Because of that, the default model always suggested kind of this red route. This is just shown as an overlay on Google Maps, instead of just driving straight through, which is actually like a super narrow road. You don't want to drive there. And if we instead learn from human behavior, we get something that is able to point out these little mistakes in our data set. There's actually not that many. It took a while to find those. But it's really interesting that you can use a model to understand human behavior to then go back to your data and say, like, maybe not all of my data is correct. Like, as I mentioned in the beginning, it's a very complex problem where data is being collected at a very large scale. There's confounding aspects on various parts of this problem. So it's really nice to actually find a mechanism that's somehow data-driven, that enables you to investigate your data, also somewhat scalably. The other, yeah, go ahead.
Data-wise, what you have is someone wanted to do the journey from A to B, the recommendation that Google Maps gave them, and what they actually did.
Without the recommendation.
Okay.
We effectively just have A to B, and then we see where the person drives.
Okay,
It's interesting that if you have data where you would also have recommendations from Google Maps, you could do other interesting things in the space of preference learning. But what we have right now is just the trajectory that somebody was driving. Okay.
Do you have to? What if people are using Google Maps and just all following this bad route? Do you have to get rid of that kind of garbage data and just focus on the non-Google Maps stuff? Otherwise, it's just learning on its own bad data. And
that is a super complex problem that, like Matt and in particular the folks that supported us on the side of Google Maps know more about. It's a problem that they generally encounter when they want to understand how to optimize. They generally need to understand when they want to optimize the system better. I can't say how we exactly do this, but there are ways to improve the data quality. I think I would say it's always a way to mitigate it. It's not a problem that you remove. It's just a problem that you reduce.
Mm-hmm. Okay, yeah.
But it's an important point.
Yeah.
Coming back to analyzing data, I wanted to throw this slide in there, which has actually nothing to do with the project. But what you will see in there is some of my PhD work, which back then when we published it, we did inverse RL for self-driving. We had like scalable data. We had 10,000 trajectories. We were super happy. And we learned a cost function based on that. On the left side, you see kind of the manually defined cost function based on some features from a LiDAR scan. On the right, you see the learned cost function with the same input features. And the fun part is we can focus on just the stairs. You can see the top right of each image. You see the picture of the front-facing camera. You see there are stairs just in front of us. Now the scripted cost function, based on the way that we describe something as like height change in a cell shouldn't exceed this and that threshold, said stairs are traversable because of the slope of the stairs. If the stairs would have higher slope, then you couldn't drive them. But sadly, these ones were not filtered out correctly back then. And the fun part is just if you just, instead of manually writing those and then testing those manually on your data, just learn them in the first instance, you don't get those issues. It's also not perfect, like the first bit of the stairs might actually not be traversable, but you get a reasonably good representation of what is drivable, purely, or what is likely to be driven, purely based on your driving data. You don't have to craft these anymore. Similarly with some obstacles in the bottom example. Now, if we look back at Google Maps, this is our world. Actually, it was not run on the whole world. It was run on a couple of metropoles back then. And you see the improvements for each of those cities in comparison to like the baseline numbers that are given by engineers, which actually took a lot of time also to craft. So it's a comparably strong baseline, but it's actually quite interesting to see how much the improvements can fluctuate based on the quality of that baseline. Maybe in some cities that was not extremely well tuned or tuned for another city and applied in this city. Based on the quality of the data, where we have higher quality data, we can learn a better preference model. And I'm still not sure why in Kyoto, but Kyoto is fantastic for us. We get super gain. While like Lima, actually, we just get 8%. But overall, we've seen, like, what was it, like a 16 to 24% worldwide improvements. And this is, like 24 is on, I think, two-wheelers, 16 is on driving. It's also nice to see that we get bigger gains for more, let's say, environmentally friendly ways of transport. But it also is connected to the part that just our preferences as cyclists are maybe a little bit more complicated.
Yeah, I was just wanting to say, I assume if your map's perfect, the planning algorithm that the engineers have used to calculate the best path is quite good and might be pretty optimal. So is it mainly that the maps themselves have these artifacts like the gates, rather than that the planning algorithm itself is actually not very optimal?
I can disentangle that a little bit more. Like the planning algorithm itself, like whatever complex and super efficient version of Dijkstra or A-star that is, we're not touching. We're touching these like preference numbers that the planning algorithm uses.
So I mean the improvement you're getting here relative to whatever that planning algorithm is, like this 18%, 20%. Do you think that's mainly improving the planning algorithm, or do you think it's because you're actually now learning the map better?
We're learning preferences better, but how noisy, like how much the impact of us being able to like handle noisy features is better, or how much of an improvement there would be if all the features would be ground truth, like the issues with the gate and so on would be disappearing. That's something we don't know. Yeah, at least I don't know.
Yeah, sort of blurs into one, doesn't it?
Yeah. Because we're unable to disentangle that. Now you could go back and take our model and kind of flag everywhere where that model disagrees with human predictions, and then manually check all of those. But that would be a lot of effort. Flagging them is easy. Understanding those discrepancies is then harder. But it's an important question, definitely. All right, let's look at the time. Timing is good. Let's move on to the second half of the talk. So I've been talking before now about RL's ability to use broader datasets or to extract different information out of datasets. Now we'll talk quickly about the point which most of you are probably here for, about robot soccer, in particular about RL just as a data generator. But before we talk about robot soccer, I wanted to quickly signal boost kind of one of our projects that Mohak Bortwash has been leading in the context of applying RL directly on real-world data. So there are many systems where it's super hard to set up a simulator. And this is kind of a proxy, a toy example for those systems. With fantastic work from also Jonas Buchli and Thomas Lampe, this has been set up. And it is a kind of aerodynamic setting where you have a couple of valves through which you can blow air. And you can control via those valves, for example, now the position of one or multiple balls. Output space is those valves. I don't know, I think each of them is a continuous value. And just safe space is, for example, the images of the setting that you have here. And then you can figure out different things like specific positions for those balls, figure out specific orientations, juggling, speed of the balls, and just to create a couple of tasks to investigate that setting and to investigate how well we can do RL on real-world data. I highly recommend the paper below. This is going to be presented, I think, in about a month at L40C, just next door in Oxford. But then let's continue on to robot soccer, where all learning happens in sim, and we get just an enormous amount of more data. Again, this is presented on behalf of all the amazing people on this slide. In particular, Thomas, Ben, Guy, Sandy, Giovanni, who have been really driving this project over multiple years, and many others on this slide. Our motivation to begin with is that, like, we're excited about robotics. We're excited about robotics because, for many of us, AGI does not mean that we stay fully in simulation, or does not mean that we stay fully digitally. We want to take over not just tasks that are digitally solvable, but tasks that we really, like in our daily lives, do not like to perform, many of which are physical. Standard examples that you probably don't need to hear, but it's dishwashing, laundry, anything that you really have, which is repetitive, which puts a large strain on your body. That is something that we want to automate, that we don't want to do, that we don't want another human to do, that we actually want to have a system, a machine to do. We can't right now test on all of the different tasks. I mean, we figured out a task that has many aspects of the broad space of tasks that we're actually interested in. And we went in the end towards soccer. Aspects that we care about is the incompleteness of observations. So the last iteration of this project now purely works on like egocentric cameras, on-body perception, on-body compute. We care about low-level exact motor control, multiple timescales as well. So we care about being able to score the ball, but also interaction between different players, competition, collaboration, everything that kind of emerge here. And also we care about, since we apply this on real robots, about robustness and about safety. We don't want to be able, we don't want to have to repair our robots continuously, which is actually still very hard with the involved hardware that we had here. But there were some advances throughout the project that made this a lot easier. You might have seen this work quite a couple of times over the last 4 years maybe. These are the initial results that we had on hardware. I think 2022, 2023. It's very interesting about how agile this gets. I'm talking in a moment about how we get to the point that we get these behaviors. It's really interesting how agile it gets, how smooth we get transitions from behaviors like just getting up, then moving forward, scoring the ball, blocking the opponent's ball, planning a little bit ahead, at least in the setting. It's still 1v1 here, but a lot of behavior emerges very naturally throughout our training. This is, however, also to emphasize, not the full robot soccer setting, not the full RoboCup setting. This is right now just 1v1, and here in particular it's based on mocap and perception, in motion capture. markers on our robots and lots of cameras. Now, yeah, you've seen this before. There have been a couple of papers. In particular, earlier this year, there has been the Science Robotics paper. I think on Archive it's been at this point for over a year. So you might have seen that work even earlier. And there was a lot of great coverage. It was really interesting to see the public react to this work as well, and to see what people are most excited about in terms of one aspect that is actually quite good for these robots in terms of what we get with training via RL as robustness of these systems. Now, this is something that you might have seen if you were at ICLR earlier this year. This is the first time that we talked about this work. So it's really fairly recent, and you can see that these tests have something different from our robustness tests in the first one, which is suddenly we're inducting with the perception system of the robot, not just with the control system. We can print out objects and see how it reacts to a printed opponent. We can give it more balls. We can blow up the balls and give it a basketball and see what happens. It's actually interestingly robust. I'll come to that later. But I'll first take one step back to just lead you through the history of this project. About a couple of years before 2022, we started working in the space of soccer. There was even more before the humanoids. There were little balls with arms in a much simpler control space. But this was the first work that kind of pointed towards applying it on robots. This is a 2v2 example. The top one is never transferred to the real world. So the humanoids are not completely representative of robots that we had access to at that point in time, but somewhat representative of a humanoid embodiment. Very high-dimensional action space. At that point, each of the players got what is the equivalent of mocap information, like exact state information about everything, about the opponent, about the ball, about the gate, where they are, all of this. And then we moved forward. This was the Science Robotics paper just this year, where we really apply stuff on real robots. And yeah, working with real robots is hard. The saying of, if during your PhD you touch a robot, you add a year to your PhD is still semi-accurate. So this is just 1v1, maybe for that reason. It's super hard, you need to repair a lot. But it's still the same training process, more or less. It's still training in simulation. It's still really large-scale simulation. It's still, in this example, state-based perception, ground truth. You can see probably the little markers on the robots on the ball. So there's a lot of engineering effort that goes into enabling ground truth state on a real robot. This instrumentation of the environment is generally something that we don't want to do, but it's the quickest way, or it was the quickest way for us to get something working. Now, just since May, this is now out as a preprint, we have extended that by actually not really changing training that much. There's a couple of things that I'll be talking about in a moment, but it's really still training in simulation, applying in the real world, but we've removed all of those cameras. We removed the trackers. The only thing why we still need trackers now and then is to evaluate those systems to see how much they score in an automated way. But training and perception of the agents does not use it at all. Let me quickly talk about the two last settings that we had. The first one was before with the mocap system. I actually have no idea of the number of cameras right now. It's somewhere between 8 and 12, I think. Lots of markers and a specific vest on the OP3s, on the humanoid robots on the ball as well. There's a couple of things just to make robotics experiments easier automated, like having RAMs, the ball always comes back. These kind of things. You don't want to interact with your system continuously. You just want to evaluate agents. Even worse if you would want to train in that setting. But here, training is fully in simulation. The main rewards are for scoring, but actually there's about 8 others to make this thing work well, to not break the knee joints, to not run into the opponent, to reduce the challenge of exploration in the setting. And the whole thing is in position control right now, 40 Hertz and 20 joints for each of those robots. What we've done now is that we keep this fairly similar. We remove everything that's mocap. By removing everything that's mocap, we say we need a different source for a lot of the perception. We need to know where the opponent is, we need to know where the ball is. To do all of this, we rely right now on onboard perception and onboard computation. So just like before, there was some proprioception about joint angles and so on, but now we additionally use the camera. There's one front-facing camera that you See about here, that's actually that has a couple of head joints, so you can move the camera a little bit independently of the body. Means you can move forward and look to the side, which is quite nice. And now, because we work with vision, we also need to train a policy that transfers to vision on the real robot. So our rendering in simulation changes slightly. We actually need rendering for the first instance. In the previous case, we never needed rendering in simulation. We just had it for investigating what the system is doing. We're training with surprisingly low resolution, it's like 40 by 30. There are many reasons when you would need to scale this up. For us, it works very well for this particular task. And we want to compute everything on board. So the lower the resolution, the cheaper this gets computationally. And just to quickly show the results again, you see at the bottom right the horribly wobbly and noisy perception of those robots. It goes so far that I don't know if I would be able to solve the task from this perception myself if I would be the robot. It's fascinating that it is possible, however. And there are many aspects in terms of working with real cameras that make this hard, where we're up to a point surprised by how well our agents have generalized. I'll talk a bit first about how we do rendering now. So we need to have something that looks approximately like our labs. What we do is actually we collect a bunch of neural radiance fields. We don't just collect one because we're really bad at calibrating them. So we collect a bunch of them and we just randomize over them throughout training. You can see it as just another form of domain randomization. Usually we would estimate physics parameters and then randomize kind of around our estimates, or maybe do some other randomization of the patterns when we render something. For us, it's just we collect a bunch of nerves, we randomize across them. Works super well. And it's actually quite simple. There's good infrastructure right now for doing nerves that we didn't need to design ourselves. Go ahead.
So that's really interesting. So rather than just creating a simulated environment, using computer graphics, you created a real-world nerve and use that. It seems it's quite a simple environment. It seems like something that you might be able to just create a model of and then just render using normal simulation. So did you try that and found it wasn't realistic enough, even with a bit of randomization?
So there's always multiple aspects that lead you to a place in a project where you are, in particular if you had other projects before. We had good infrastructure for that. I'm not saying it's the only way to do it, definitely not. But it worked really well with low effort. One of the problems that I would see with a simpler method is kind of, if you sometimes see the backgrounds, right? Sometimes you see like there's curtains, chairs, and so on. We actually move them around a lot. We don't remember where they are. We have nerves with all kinds of configurations, just not because we wanted to generate them, but because that's what's happening to the background. By doing it in this real to sim driven way, we collect all of that variance, all of that change automatically. So there's really interesting work from other teams doing sim to real in a way for robotics. There's like David Skalmus's work and so on. And there's different ways to realize the perception part of that system. But from my experience here, if I would be starting a new project, I would be going that way right now.
Okay.
Again, it's not the only way, but it worked really well. It was surprisingly simple to set up. Go ahead.
How much does performance drop off between training and testing?
Between in sim and it's actually not that much. Scoring is still surprisingly good. One of the things that you see is you see a little bit more falling, so these dynamics seem to be harder. In general, how would I surprise? There are exact numbers in the paper that you can find. I think that's the best way. There was not too much of a difference. There are a couple of aspects that really become harder in the real world. But in particular, so what we did, I don't have slides on this right now, but we did also some penalty shoots. Like agent lies somewhere, agent goes up, goes to the ball, and just shoots a goal. That works effectively on par with sim, which was great to see. The game is a little bit harder with an opponent that is also in there. Maybe this is actually a good point to talk about that quickly. I'm talking right now here and about the simulation of the environment, right? You see also there's no ball, there's no robot. Ball and robot are dynamic. We can't just use a standard nerve that would be static. There are ways probably to do that well in the space of nerves as well. Back then we just wanted to have something that works quickly. So it's actually an overlay of Mojoko on top of the nerve. So you kind of have the robot from Mojoko, the ball from Mojoko. Some aspects of the robot and the ball are randomized because like the Mojoko rendering is very inaccurate for the robot in particular. but it seems to be sufficient. You see also later on that like interaction with the opponent is good in sim, like you don't run into the opponent. So somehow it generalizes from whatever it's seen in sim, even if it is a somewhat inaccurate rendering from Joko. Quickly to talk about how we make this work as like a second stage in this. The pipeline that we used for training by RL is very, very similar to what we did in stage. And this was largely for practical reasons. It was already there. Why change what already works well? There's a couple of things that actually did not work well. One is obvious. In your environment, you suddenly need to render. So we changed the environment. What we also realized is that, well, training DeepRL policies from vision is hard. It needs just much more data. Particularly if we start, imagine you just do a ResNet, a couple of MLP layers afterwards. Do something fancy, maybe a VIT. Does not work on the robots. But for now, whatever you train it with DeepRL. And what we've seen is it converges at somewhat suboptimal performance, no matter how long we run these experiments. So the first one were run for a couple of weeks, effectively. What we found out works really well is the relevance of the knowledge that this agent has generated. But we want to have that knowledge in a way that it doesn't define our behavior. You could imagine the knowledge is extracted in the policy, is extracted in a critic if you have an actor-critic setting. But we actually reset both of those. If we fine-tune them, it would be just like running one experiment longer. So what we figured out is reset the agent so that it still has all its representational capability to change, but also has all of its ability to explore, all of the randomness in the behavior in the beginning. So we just restart experiments a couple of times, but we keep data around. This is what we call a replay across experiments. There was a great ICLR paper led by Dhruva Tirumala. There's a separate website if somebody's interested. I can point you to it later. But it's really just seeing the off-policy RL mechanism as more of a workflow thing. Like when we, as RL researchers, do experiments, we don't do just one per domain. We change hyperparameters, we change this, we change that. And what you can do is just keep the data from previous experiments around. It's usually super useful. And the simplest thing possible. I wanted to say stupid, now I'm going to say the stupidest thing possible really works. If you run off-policy RL, always keep the data around. We mixed it with 50-50. There's a hyperparameter, how much of your data do you want offline, how much do you want online. You can play around with that. You can boost performance a little bit. If you don't care super much about the data, 50 works, just half-half. Wonderfully simple. We do this a couple of times. Instead of our performance stagnating, we get much better scoring. In particular, we get really good competitive performance, like playing against another agent. After we've done this, transfer to real world, zero shot again. There's no real world data involved other than in shaping the nerve. I'm really curious about what we could get out of real data additionally, but surprisingly, this simple approach with just very limited feedback from the real world has sufficed for us. I can show you some results in simulation. Let's do this very quick. You see very nice competitive play. It's not as dynamic as from state. The problem is harder. The agent does not know its exact configuration that well. But what we probably all really want to know, or really want to see, so let me zoom in a little bit, is how this looks in the real world. So again, you have on the bottom right, you have the perception of the agent. In the real world, this is definitely much worse than in simulation. You will see blocking behavior emerging, scoring behavior emerging. For the sake of time, I'll just go forward. All of those videos are also on our website if somebody's interested. The interesting thing is not just what the agent does, but how it does it. So what you can do after training the agent is looking at its representation. Somewhere in the agent, there's actually a way to integrate history. For us, that's an LSTM. And somehow you might imagine that the agent actually needs that way of using history because the ball is not always in view. The whole setting is partially observable. It doesn't see the opponent all the time, it doesn't see the ball. It would be good to know about the ball at the time when you don't see it anymore. And we can actually now look at what this LSTM represents by training some kind of additional predictive probes on top of the LSTM without back-propagating through the rest, just as an analytical tool, not as a tool to change the agent in any way. And then we can actually see very nicely here in sim when the agent gets up, for example, that it slowly estimates its own position. As soon as it sees specific parts of the environment, it knows exactly where it is. It's more interesting. Wait, I think this is ball prediction, yes. So you see in the beginning that it doesn't see the ball, it walks around, it's kind of a search movement. You can actually remove the LSTM and see what an MLP without history does, and it does a lot of this circling. As soon as the ball is gone, it can still solve the task, actually reasonably well. But it's somewhat inefficient because it always has to search the ball again as soon as it loses it. And we can see what history, what in particular in our case the LSTM gives us. It could be any other way to integrate history information. It could be a transformer. Again, hardware constraints on our end led to an LSTM just working quite well. We can look at the penalties for the sake of time. I'll just go quickly once in there. It's effectively really just situations that the agent was never trained for. Oh, it's super excited. It always gets up at full speed. But because it needs to have these like move to the ball and scoring behaviors throughout the game, we can just test them individually as well. Even though it was never just tested on this task, but it's a part of the other task effectively. Works really well. What else can I say? It also hits the posts quite a bit, but let's see. I was hoping I can show this video. It's quite interesting because maybe I can't. Because in this setting, what you can look at is actually, okay, let's see, let me go a little bit forward. You can see how vision, the perception of the agent works, how robust it is to specific aspects. What we can do is now, so that there's a reward term in there that says don't crash into the other agent. So what my colleague here is doing is put the other agent in front of it and see if it moves back, if it doesn't walk in there. And it's actually very careful. It's definitely not the solution for safe robotics to just put a reward term in there, but in this simple setting, it's surprisingly good. What we can also do is include the vision, but I think what is actually even more interesting is that real-world adversarial examples exist. We can just print out a ball and see if the agent reacts to that. And it's surprisingly, from the feature instead of the bug side, it generalizes really well. It considers this ball to be a ball. Sometimes when there's a real ball, it actually instead focuses on the real ball. There seems to be still a difference. I mean, we printed this out very quickly. It has a white frame around it. It does not look super accurate. But it generalizes surprisingly well to it. We can do the same thing also with an opponent, which should be somewhere here. And it will step back. It will try to not run into this. There's two more interesting examples I think that we should talk about. One is you can just, by training in vision, you can enable it to generalize more quickly. So you can add more balls. You can actually also add more opponents without training with it. If you do this with mocap, you somehow need to have a feature space that is invariant to the number of opponents. For vision, that input space, at least in the first instance, kind of somewhat is. Oh yeah, and because of the resolution of the camera, we generalize to many objects, including the fox. So if there's a fox in the ball, it will fill the ball. But if there's just a fox, you can actually score a goal with that fox. The dynamics are super different, as you see. This thing doesn't roll. It has incredibly high friction. But by just always correcting, by having these fluid motions, it falls, it goes back up, it kicks again, you can solve the task even if you change it that much, without ever training for it, without ever changing our randomization parameters this much. I realize we're kind of running over time. Okay, I'll do 2 slides and then we can go into questions. Let's do this very quickly. One aspect that I've been talking about a lot throughout these examples is the ability to transfer in RL. To have one data source and somehow apply to another setting. Like the simplest case, the most common case right now remains sim to real. You somehow need to transfer to the real system. And we've recently done a taxonomy, a survey of this kind of work. If it's interesting for you, have a look. If you have any feedback, please reach out. And finally, yeah, RL remains still very relevant for robotics. Where it remains relevant has changed slightly. It's maybe not so much anymore about training from scratch and getting the best behavior in that setting, but really making use of all of the other sources of information that we already have. That means we improve on top of existing systems. We can do data generation with RL, but maybe we actually bootstrap that setting with access to another data set, like we did here, or with access to any kind of pre-trained foundation model. Think VLMs. What is possible in that space? Interesting regarding data generation, RL does not always have to rely on rewards. That is one of the aspects that I also wanted to emphasize with our work on inverse RL. You can use RL mechanisms to still optimize other objectives that don't have to be conveyed via rewards, that could be conveyed via a easier to represent source of information for humans. Like, it's easier for us usually to give a demonstration than to manually write down a reward, test, and see if it fits. The other aspect is data usage. That was pretty much the first half of the talk. We can expand our use of other data sets. We can use in quote-unquote suboptimal data, as long as there's some informative aspect in there. And we can extract other bits of information from the data. So for example, if we look at the application of inverse RL for maps, we actually don't want to change the maps route recommendation system. It's super complex. It's really well optimized. It's also really cheap to run computationally. Imagine we would train a policy. At every step of the way, you would need to execute, perform inference on like 100 million plus parameter model. It's possible, but it's super expensive. Now imagine when you actually have a reward function, we can use the existing planner. All of that inference time optimization, all of that deployment optimization, we don't touch. It's actually really good. This is something that we should value. At the same time, even one step further here, if we work on the problem that we see with maps, we can throw our model away after we've executed the final time. We only need the values. We only need the final preferences for specific segments. We don't need to execute even for planning our foundation model during runtime anymore. So it's really cheap. It's just accessing numbers that were stored once. So you train your model, you generate the final preference numbers, then you can actually bin your model. That's a super nice aspect if we exploit specific properties of our problem. So for robotics, that won't work instantaneously, at least for many formulations in robotics, but for navigation, it worked really well. And in that case, extracting the reward function via RL was so much more effective and efficient than training policy, for example, via now. Imagine, you could have taken the same data and just run VC on it. A couple of relevant publications, if anybody's interested in them. Otherwise, I'd be happy to answer any more questions. Thanks for your attention.
Thanks so much, Markus. So we have time for some questions if there are any. Yeah.
Hi, thank you for the talk. It's very insightful. Now, earlier when you were talking about the nerve environment, you were talking about how the performance plateaued out after essentially a certain amount of time. You couldn't improve it after training. Was it possibly due to the learned representations having a poor understanding of, let's say, physical constraints, and that's what you saw in the adversarial example as well, with the forks or the printed ball? Was it like due to the nerve generation probably having a poor physical constraint, like poor physics generation, just because it's just low resolution?
It's a very good question to start with. There's different aspects to any answer to that. The main thing is that, so the nerves are fixed in any case. It's just about the RL system. It's about resetting the training of the RL agent. But then there's two aspects that might matter that we didn't investigate. There's a lot of recent work that's really quite interesting in the context of plasticity loss in RL. Like the longer you train, the more you add later on tasks. Does the agent actually have the ability to still adapt? Imagine like we train deep nets. There are some non-linearities in there. They actually sometimes tend to saturate. If it's saturated, it's harder to change. The other aspect is the ability of an agent to exploit, to still generate diverse data, because if you always generate the same data with RL, you can't improve anymore, except for if your environment is stochastic. But even that. Anyway, so you need to be able to generate rich, diverse data to get a good signal for RL. And that, in conjunction with the changing of the parameters, renders just resetting parameters quite good in our system, like resetting the whole agent. There's another interesting question connected to that, which is, what if you can't reset your agent all the time because it's computationally too expensive? Our agents are for this, or for the soccer task, are comparatively simple. They're comparatively computationally cheap because we want to run them on hardware. Right now, there's a lot of really interesting work going on in training more and more complex models on larger and larger data sets. Aspects that get really computationally expensive, where you might not be able or might not want to do that anymore. Then you need to figure out better ways to do this.
Ivan.
Hi, yeah, thanks for a great talk. So nerve reconstruction seems like a good way to close the subterior gap for vision. But what about also the dynamics? I mean, like the friction of the surface and the mass of ball properties of the joints. Probably that's quite a hard gap to close as well, right? So, what is your insight about how to do this? Is domain limitation enough, or do we need something else as well?
For this setting, it was enough. But okay, let me put a disclaimer in front of that. It was enough, conditioned on having our fantastic engineering colleagues in the beginning do good sysid. So it's not just about randomizing everything. You can't randomize over the whole space of possible parameters. You need to know where you need to randomize. But then it works surprisingly well. There is one more question connected to that in the context of if you randomize too much, you might, imagine you don't have a way to have history in there. Imagine you actually train one agent that's conservative across all of those settings. Then you might actually lose performance the more you randomize. Just because it needs to work for like a friction coefficient of 100 and 0.1. Then you can just imagine that this gets hard. It will still probably in many cases somehow work. It will be just suboptimal. There are interesting methods on figuring out how far you need to randomize in an automated way that are interesting in that space. Peter?
Thank you again for the talk. And I wanted to ask something about the inverse RL and Google Maps. I was wondering if and how you're handling the fact that people change intentions. So even the same person, I don't know, when I want to go to dinner, I might want the fastest route, and on Sunday it's nice weather, I might want to take more of a detour. So do you have like an input in the model? So
We don't. It's a very interesting thing. It's like you could do a lot of personalization, very useful personalization in that space. At least here we don't do.
So you think you can cover, like there's a big majority of the times one uses Google Maps is for the intention of
It's
an
average
average,
behavior.
yeah.
It's average. But you're fully right with pointing out that aspect of the problem that we ignore.
Thank you.
Oh, Andy.
Keeping track.
So yeah, really nice work. I mean, clearly it's a toy problem here. So what have you learned that where with this sort of method has helped the most? I mean, is it in the perception? Is it in the control? Is it or is it somehow in the whole system? I mean, you do this thing of, for instance, the robots have got big feet, for instance, and I assume if they had small feet, none of this would work because they wouldn't even learn to stand up. So what's the real research goal? I guess that's what I'm asking.
Specifically for the like robot soccer scenario?
Yeah, I guess that's soccer.
Yeah. I think in particular the ability to take a good starting point and improve on top of that. So here our starting point was like all previous experiments, but really the ability to self-generate better data is and have that data somehow be rated as like what of that is good, what of that is bad, is going to continue being useful. Now, like there's a lot of work where also in robotics we have larger data sets to start from, and it's something that we shouldn't ignore. But really building up on top of them and having a way to generate data that does not require human labor in the same way that like learning from demonstration does, when you need a lot of data.
But I'm questioning more, do you even really need a lot of data for this task?
For this task?
Yeah.
Yes. Still sadly.
But which part of it do you need a lot of? I mean, for instance, learning the tactics in football that you have to, stand with the ball between you and the goal and kick forward. That's not something you really need a lot of data for. That could be expressed in a few equations, couldn't it?
Yeah, it's this.
I mean, I could hand design that with a few lines of code, for instance.
So this is for me another interesting thing where maybe so. This is still without a lot of that behavior that you described right now because it's just two opponents, like one opponent on each side. Like collaboration and more complex competition is not emerging here right now. What is for us hard to get is like the exact mapping of a very complex perceptual space to complex behavior under that. I think we can bootstrap with that with other sources of knowledge without information that you described right now. Like other aspects of coordination can be described from, I don't know, you could also take other data sources like a related team at DeepMind recently was looking into more high level, how do soccer teams interact and train effectively coaching agents based on that.